space is a list of all the possible outcomes. We're going to be studying probability, and you know some basics about probability. You know that, like, you take the number of ways something can happen and you divide it by all the ways, all the possible outcomes, not just what you want to have happen. So sometimes mathematicians use sample spaces, they list them out, and they can see how many total outcomes there are and what their desired outcome is, and they can count those things up. It's just a way to count things, or a way to see what's possible. So our first example says, in an experiment, there's 3 coins that are flipped. List all the possible outcomes in the sample space of the experiment. If I were flipping 1 coin, what would be my outcomes? Heads and tails. Okay, so we're going to list what are the possible outcomes if you're not flipping 1, but you're flipping 3 coins. And just to make it like less writing, I'm going to use H and T. So I'm going to give you a minute, see if you and your pod can come up with a list of outcomes for flipping 3 coins in terms of H's and T's, and we'll see if you've got them.
Oh shoot. Yes. So it does count if it's like heads, tails, tails, and then it's heads, tails, heads, tails.
You're right.
I got
Miss Husky. Okay, I'm going to list them mine. Heads, heads, heads. Heads, heads, tails. Heads, tail, heads. Tail, head, head. Okay, tail, tail, tail. Tail, tail, head. Tail, head, tail. Would that be head, tail, tail? You have 8?
Yes.
Okay. If you don't have 8, you're missing one. See if you can find it and let us know if you can. There's 8 total outcomes. Does anybody know how to know that there are 8 total outcomes without listing them all, Logan?
You could take if they're all the same they're all the same thing. You can take the number of possible outcomes from 1, and then its exponent would be however many of them there are.
Okay.
Since there's 3 coins, it'd be 2 to the third.
Okay, because they all have the same. Or you can even break it up, like if you don't want to think about the exponent there. Like, what's the number of outcomes for the first coin? 2. And for the second coin?
2.
And the third coin?
2.
2. So each of the 3 events has 2 possible outcomes, and then you just multiply all those together. We talked about that in the dice experiment, right? But if you're rolling 2 6-sided dice, it's 6 times 6, or you could use 6 squared there. Okay, excellent. So we kind of already know that there should be 8 total, and we've got all 8. Okay, great. Now I could ask questions like about probability, just to kind of give you a heads up as what we're going for. Like, what's the probability that you flip 3 heads? 1 out of 8, because there's only one outcome that is 3 heads. What's the probability that you flip 2 tails?
Only 2 tails or just
3 out of 8.
Exactly 2
Oh,
tails.
exactly
Okay.
2. 3 out of 8. 3 eighths.
3 out of 8.
Oh,
There's
yeah.
3 of them there that have 2 T's. What about at least 2 tails?
2. Half.
There's half.
Half. Yeah, because there's 4 out of 8. You'd add the 3 tails with the 2 tails. Okay? So you can use sample spaces to calculate your probability. All right, just really quickly, we'll review the dice because dice happens quite a bit. And on this first one, if you roll a 6-sided dice, what's your sample space? 1 through 6. Okay. A lot of times mathematicians, when they list sample space, they use the squiggly brackets. So it's just like all these things inside my brackets, these are the members of the sample space. I'm not too picky here in this chapter if you use the squiggle brackets or not. It just really depends. Next year in pre-calculus, when you do probability, they'll show you those brackets again. Now, we already should have listed the possible outcomes for rolling 2 dice on Friday, but I'm going to show you just real quick an easy way to make that list of possible outcomes in case you ever do need it again, or if you get stuck on a quiz or test, you can always easily make the list. How many total outcomes are there? 36. Here's how I make a quick and easy list for myself. I make one column of 6 ones. This is my first die. What if my first die is a 1? Then my second die can be a 1, 2, 3, 4, 5, or 6. Oops, I had 7. Is that true? Mm-hmm. Okay, so these are 6 possible outcomes. And then I can make a column of 2s. And my second die could be a 1 through 6. And I can repeat that for the other columns. Now, I'm hoping that moving forward in the chapter, you're not necessarily feeling the need to always write down all 36. But I like to, at the beginning of the chapter, write it down or have you look at that a few times just to kind of cement some of the things that we talked about on Friday. Remember how on Friday I gave you one colored die and one white die? And we kind of made the point of like, okay, a 1 and a 2 is different than a 2 and a 1. And we can see this in this sample space because we're listing both of those out. Versus if you took those 2 die and you made them both a 1, how many ways can you roll 2 1s? Only one way. How many ways can you roll a sum of 3? 2, because you could roll a 1 and a 2 or a 2 and a 1. That sometimes just really like messes with people. They don't count the 2 and 1 different than the 1 and 2, or every time they see a double, they count it twice. 1, 1, 1, 1. That's one way. So this kind of cements that, and you can see all the doubles are on this diagonal, right? So there's 1/6 probability of rolling doubles. And then everything else has a matching pair. Okay. Moving right along, here are some basics about probability. So I've got the number line underneath my shade there, so you want to try to find a place to plug this information in on your closed notes. The definition that we generally use for probability is just to say that it represents the likelihood that an event will occur. And we have a notation, this P of A. I would say just think about that notation as like a function notation, f of x. But instead of calling it f for function, we call it P for probability. And the of A, this would be like the probability that event A will occur, but you could put anything you want in there. Okay. So if we wanted to do like the probability of rolling a single die, what's the probability of rolling a 1? 1 out of 6. Okay, that would be for like a single die. Or in that other example with the sample space, I could say, what's the probability that we get 3 tails? And we said 3 out of 8. Or we could say, what's the probability of a snow day tomorrow? And you'll check your snow day calculator, right?
Yeah.
Nice.
Oh, that was weak.
Oh, yeah, that's 50% yes.
Yeah, but also 50%
Good.
Let's not be negative.
I'm not.
Okay, the point is you can put anything you want in there. You can put words, you can put sentences, like just to describe what your number represents, right? It's the probability of this thing that I'm describing in there. Okay, now probability exists on the continuum from 0 to 1 if you're working with decimals. If you are thinking about percents, that would be 0 to 100%. But never should you ever give me a probability answer that is negative. That doesn't make sense. Never should you ever give me a probability answer that is over 100% or 1. If you're looking at decimals, that doesn't make sense. So you know your answer is not right. You should fix it. Please don't ever turn it in. I'll be hard pressed to give you any partial credit on a crazy answer like a probability of 5. It just won't happen. Now, on that number line, that's just like where you see probability. So, 0 is the probability saying that our event will never occur. So, like, don't give me anything less than 0 because there's nothing worse than it not happening. On the other side of that, a probability of 1 means it will absolutely occur. There is no question about it. It will happen. And then, of course, depending where you're at on that line, your probability is either more likely or less likely. If you're right in the middle at 0.5, like you guys were talking about, it's equally likely. Besides tomorrow's snow day calculator, can you give me an example of another event that is equally likely to occur as to not occur? A coin flip. Like, what's the probability of getting ahead? 0.5. What's the probability of not getting ahead? 0.5, right? So that has a fair probability. Okay. You probably are hoping for fair things. In the case of like a coin toss, you want it to be a fair coin toss. Okay. Next up, complement. Now, this complement is spelled differently than the complement of you look nice today. So I'm going to write that one up on the board. Just out on my keyboard, please. An I is a complement like, hey, you look nice. A complement with an E, what we're talking about in math, is the probability that something does not occur. You can think about a complement almost like the opposite probability, or the probability of the opposite, I suppose. There is a notation for that. It looks like A prime, so that's just an apostrophe. I know you've seen that notation before in geometry. And you can read that one of two ways. You can call it the complement of A when it has the little prime on it, but more generally, you're going to hear me say not A. So I know in geometry, when you did logic, you used the squiggle for not. Do you remember that? Not P, not Q, that kind of thing. But we're going to put the apostrophe or the prime and then read that as a not. Okay. So let's see. Probability of snow day tomorrow, let's say it was 0.6. We'll go a little high, be a little optimistic. What's the probability of not a snow day tomorrow then?
0.4.
0.4. So the complement is always the other probability, the other part that would add to 1. So to calculate a complement, throwing darts over there. To calculate a complement, the probability of not A is equal to 1 minus the probability that A does occur. You know, what's the probability of rolling a 1 on a die? 1/6. What's the probability of not rolling the 1? 5/6, because it's the probability of rolling a 2, 3, 4, 5, or 6. Okay. Now, sometimes you can use the complement to make your life a lot easier. Like it might be easier to actually do the not version than to count up all the ways that something can happen. Count up the ways that it can't happen and then subtract. Okay, so that might be easier. Okay, moving right along. Calculating probability. You know, probability is just the number of ways that an event can occur divided by the total number of outcomes possible. I'll often refer to that numerator as favorable. So I have that up there. I always say favorable over total. When I say favorable, I mean like for the probability that you're looking for. So if I was doing like that example with like the probability of 2 tails. Favorable is having exactly 2 tails. So I just have to count up how many ways I can get exactly 2 tails. And then divide by the total outcomes possible. There's 3 basic types of probability that we're going to be looking at: theoretical, experimental, and geometric. And we actually, like in that dice activity that we did on Friday, we kind of like dipped our toe into theoretical and experimental. Theoretical is what should happen. Experimental is what does happen. And then geometric probabilities, I have a little extra information on the next slide that you can kind of squeeze in that margin if you want. Geometric probabilities that I give you are generally going to be probabilities related to like shaded regions or areas. Okay. So I don't have a particular place for you to write this on the closed notes, but if you want to, you know, remind yourself or give yourself some idea here. If you're ever asked about the probability of a shaded region or a colored region or a particular area, you want to take that area that you're looking at, in this case the shaded area, and divide it by the total area possible. Those are really like the geometric problems that I'm going to give you. Make this smaller for you. So I don't know that you necessarily need to put these on your closed notes. This is like an individual thing. I'm just saying I told you once what the 3 basic area formulas are, and I don't need to tell you again about a rectangle, a circle, or a triangle. Okay. So if you want to write them down, you can write them down. If you feel confident, you don't have to write them down. But I would expect you, like on a quiz or a test, like fair game, all of these. I don't need to give you that formula. You should be able to do that area. Are we okay with that? Okay. And you can do base times height divided by 2. That's the same thing as 1/2 base times height. Okay. Now, we're going to do this theoretical versus experimental piece, even though we did kind of do a little bit of this on our dice activity on Friday. So we're actually going to complete lines 1 and 2 together because that's theoretical. That's what should happen. So it doesn't matter. We don't need separate trials. We're doing the theoretical probability of rolling a single 6-sided die. And we want, like, what's the probability of rolling a 1, a 2, a 3, a 4, a 5, a 6? Okay, so line 1 is the number of favorable outcomes. So how many favorable outcomes are there on a 6-sided die for rolling a 1? 1. And a 2?
2. Or
1.
1. And a 3?
1.
It's tricky. There's one way to get each of those, right? There's one favorable side to you. And so they have what we would call uniform probability, because when we calculate probability, the total number of outcomes is 6. So it's 1/6 for all of them. And then because we're going to be doing some different number of trials instead of just 6, I'm going to go ahead and calculate that as a decimal just so I can kind of, like, it's easier to compare decimals than it will be to compare fractions that don't have, like, denominators. So that comes out to 0.16 repeating, so I'm going to say 0.167. Now, you and a partner are going to complete lines 3 and 4, and then we're going to come back and complete lines 5 and 6 together. So when you look at line 4, the experimental probability of rolling with a shoulder buddy, it should say your total outcomes is 10. Okay? So what you're going to do is we'll put you in pairs, and you're going to roll the die 10 times, no more, no less. Record what rolls you have. So if you want to use like tally marks, you can for line 3. And then you're going to calculate your individual probabilities down here on line 4. Well, you just take, like, if I rolled a 1 3 times, then it will be 3 out of 10 or 0.3, right? So you'll do that individually with your partner. Okay? And then we're going to come back together and get all the data for the class. Okay? But for right now, roll it 10 times, no more, no less. If it lands on the floor, just say what it rolled as, right? Rhiannon, I'll have you jump to the back there and join Sierra. Once you get it, you can start rolling. Don't forget to record exactly 10 times. We need data. Record every roll. You should have 10 at the end.
I'm just writing them all. I'm just writing what numbers you get. Because we're supposed to do hours, but I started to say that.
Oh my gosh, I could keep that.
So, 3 ones.
So it's 2, 2, 1, 2, 0.
Okay, I think this way more. Oh, my sugar. Yeah, 2.
You got all 10 rolls? You guys got all 10? 10. You got all your rolls?
Thank you.
Okay, you should be calculating your probabilities in line 4.
That's a different word.
What do you do? You can't say like, I should never
Okay, now let me interrupt again. Alright, you guys, for your partners, you'll all have different lines 3 and 4. And, depending on what you rolled, like if you did a 3 for rolling a 1, that would be 3 out of 10 or 0.3. That's kind of far off from the 0.16. If you didn't roll one of the numbers, you probably have a 0 there. And like there's a possibility maybe like 6 was really hot on your dice. You got like 5 out of 10 or 1/2, right? So that's an option. What we're going to do is we're going to take each of your group's data and collectivize it, and we're going to put it in lines 5 and 6. So I need one of your shoulder buddies, your rollers. You're going to be the reporter. You're going to say the number. We're going to do like 1s first, and 2s and 3s and 4s. You're just going to say the number. I'm going to add the numbers, and everybody who's not reporting will be checking Ms. Cronke's addition. Okay? So, you all know who's reporting? Who's reporting from the 2? Okay. 1s first. Tell me how many times you rolled a 1.
3.
3. 4.
2.
6. 9.
2.
11. 14. 16. 18. 21. Did I have that right?
Yes.
Okay, 21. Put that in that box in line 5. Now we're going to do the 2s.
2.
2. 4.
2.
6. 6.
2.
8.
2.
10.
2.
12. 15. 16. threes.
2.
2, 3,
Zero.
3, 5,
4.
9, 11, 12,
1.
13,
3.
16. Okay, fours.
0.
0, 1,
0.
1,
2.
3,
0.
3, 3,
Oh,
5,
Sorry.
0.
5.
0.
Of
course, Katie.
What were you guys doing?
Oh. Nobody
Okay, that's strange. All right, fives.
0.
Oh,
0, 1,
4.
5,
That's what was
7,
1.
8. Hard. 9, 9,
2.
11, 13. Okay, last one, sixes. Phew.
3.
3, 7,
2.
9, 10,
1.
11, 13, 16,
2.
18,
What?
19. Did I add wrong?
No, I said something.
Like,
Our
here's a
classic
number,
game.
she like here's a number and then she has to think of another number and say it. Like that's just like
Okay, let's make sure that those add up to, let's see.
17 or 19?
I have 19.
Oh, okay.
1, 2, 3, 4, 5, 6, 7, 8, 9. We should have 90 total outcomes for our class. Okay, so let me see if those numbers add up to 90. Success. Okay, now what I'm going to do is I'm going to take each of those numbers. I know it's kind of hard to see in the shaded regions here, but I'm going to take each of those numbers and divide them by 90. So 21 divided by 90 is 0.23. Let's see, 16 divided by 90 is 0.178. 0.178. I don't know what happened with those fours. 0.06. 13 divided by 90 is 0.14. And 19 divided by 90 is 0.21. Okay, so what I want you to do real quickly here is just like look at your line 4 and our line 6 on your paper, and what you should see is sort of an evening out. Like it's getting closer to the theoretical probabilities. And now there could be some oddball ones where you were really, really close and then we had some strange things happen, so maybe go further away. But overall, we should see it trending towards the actual theoretical probability in line 2. So flip that paper over. And just real quickly in your own words, I'll give you about 20 seconds. Answer the question on the back side. Generally, as the number of trials increases, how will the experimental probability compare to theoretical? Got a question? Oh. Brianna, what was the gist of your answer?
I think it'll get closer.
Oh, I'll check.
It'll get closer.
It should get closer to the theoretical. As the number of trials increases, your experimental probability should get closer and closer to the theoretical probability. If we were to do this again and have 180, those decimal values should get closer and closer to 0.167. If we ran it 1,000 times or 1,000,000 times, it should get even closer because the strange things that happen probably will sort of even out in the end. Okay, now run through some of the examples on the back. We'll get through as many as we can so you can work on them for your homework. Number one's a great one for us to think about. A student is taking a quiz and they randomly guess the answers to 4 true-false questions. What's the probability of the student guessing exactly 2 correct answers?
0.5. No.
Incorrect.
0.5.
Very unlikely.
1/4.
Well, let's figure this out with basic probability, right?
Yes.
So what do we need in order to do probability? The total number of outcomes. So help me out. How many total outcomes are there when answering a true-false question? True-false test with 4. 16. How are you getting that?
4 plus 4 plus 4. Or 4
4
times 4.
times 4. Or
Yeah.
2 times
2 times 4, I guess.
2 to
Wait,
the
so
power
maybe-
4. 2 to the power 4.
Okay. How many ways can you answer the first question? 2. How many ways can you answer the second question? 2. How many ways can you answer the third?
2.
And the fourth? Okay, so that's kind of like what Logan described at the beginning, right? If they all have the same amount of outcomes, just raise it to the exponent of how many there are. That means there's 16 ways for you to answer the test. Right, wrong, mix of both, who knows? There's 16 different answer keys that we could make. So for the probability of getting exactly 2 correct, we know it's something over 16. How could we figure out how many ways there are to get 2 correct out of 4? I think about this like how many ways to get 2 heads out of 3 coin tosses. What could your answer key in terms of rights and wrongs look like?
Right.
Okay, you could do right. Then it would have to be wrong.
Wrong, right.
Wrong, right. Wrong, right.
Right, wrong.
Right, wrong, right, wrong.
Wrong, right, right.
Wrong, right, wrong.
Sounds like we would. Wrong.
Wrong, right, wrong. And the opposite.
Right, wrong.
Right.
I thought incorrect last hour sounded funny, so I changed it to wrong and right. No, never change it back. That was the best. Okay, do we think we have all of them? I think. Yeah, so how many ways are there? 6. So 6 out of 16. Now, if you're leaving your answers as fractions, the only thing I request is that your fractions be simplified. So we would divide both of those by 2. That would be 3/8. You can also give me your answers in decimal form. This would be 0.375. Or you can do percent. So this would be 37.5%. I generally stick to fractions and decimals. And if the fractions are small and easily simplified, I leave them as fractions. And if the fractions are big and not easily simplified, I write them in decimal form. And I don't usually write them as percents unless I'm trying to answer a question that makes sense in percents. Okay. There'll be a question similar to that on your homework, so just kind of be prepared for that. It is very common to answer questions right away, 1/2. But remember, we're learning probability here, so really kind of delve in and convince yourself that that is the correct answer, because in this case.
Did we forget all right and all wrong?
Well, those are part of the 16 total outcomes, but see, I don't want to list out 16 of these.
Oh, okay.
These are only the ones for exactly 2 right. They each have 2 rights. So I'm not listing when I have 3 right and 1 wrong. I'm not listing when I have 4 right and 0 wrong. And I'm not listing when I have all wrongs. Or 1 wrong. Oh, wait, I already said that one. Okay, let's try another problem. Calculate the probability of rolling 2 dice and getting a sum of 5 or 12. I'm going to use my new notation. Probability. Sum of 5 or 12. Well, what do we know about rolling dice? 2 of them. 36 outcomes. I hope that you don't have to write all 36 right now. You can just write out the ones that work. So, like, how can you get a sum of 5?
2, 3.
2, 3?
4,
3,
1.
2.
4, 1. 1, 4. 3, 2.
I think that's it.
Yes.
And how many ways can you do the 12?
6, 6.
So our probability would be
5 out of 36.
5 out of 36.
Do we have to do that manually?
Well, no. I mean, like, if you can keep track of it, but know that if you get it wrong, I'll have no idea what you did. So, you know, let's show your work, but your choice. Okay, let's do example 3. Calculate the probability of rolling 2 dice and the sum is not 4. Oh, yeah, this one would probably be easier done with its complement. So to think about it in terms of complement, think about how many ways you could get a 4, right? So what are the ways to get a sum of 4?
2, 2, 3, 3, 1.
Do let's do 2 again.
Oh, I didn't see that.
Doubles only occur once and then mismatches occur twice, right? You can flip them around. So there's 3 ways to get a 4. So you might just say 33 over here, or you might write it out 1 minus 3 over 36, but those are the same things, right? And this would be 11 over 12. Okay, so that's using your complement. Work smarter, not harder. Find the probability of that a randomly thrown dart would hit the shaded region of the target below. So can we talk about strategy on this one? How can we get our shaded region?
2 quick announcements. First of all, if you don't already know, the girls' district basketball game at Lincoln Northeast today has been postponed to Thursday. Again, basketball at Lincoln Northeast today is now Thursday at 5:30. In addition, tonight's freshman boys basketball game has been canceled. The next game is for them Thursday night in the prep tournament. Those of you who are freshman basketball players, see Coach Brown for details. Thank you.
Okay, so if you look back to geometric probability, it's just shaded over total. Well, how can we get the shaded region? Okay, so the area of the rectangle minus the area of the 2 circles. And then how would we get the area of the total? The rectangle. Okay, good. So how will I do the area of this rectangle? 4 by 8. Why do you know it's 8?
Because the diameter of a circle would be 4, and 2 circles make up the length of it.
Yeah, assume the circles are tangent to one another. So this would be 32 minus 2 times the area of the circle. Pi times what's your radius? 2. All over 32. And then I probably would simplify that a little bit. So 2 squared times 2, what is that, 8 pi? That's 32 minus 8 pi all over 32. And I would guess a lot of people on this one would go ahead and do that as a decimal. If you're going to do it in your calculator, you're going to need a set of parentheses, or you're going to need to do it separately. I think it comes out to 0.215. 0.215. Okay. Now, the last example just has a table for you. So you're calculating like the probability that they like the shampoo. So you just need to do the shampoo over the total outcomes possible. And you have a homework assignment on your textbook. I'll see you tomorrow.
Bye.